Okay. Does it help if I show you the slides, or do you prefer working with the Jamboard? Which one do you think is more interesting for you?
Jamboard helps us more, I believe.
Jamboard, yes.
More effective.
Okay. Okay. So you guys don't like slides, or what?
The slides are so cramped, and a lot of information is shown at the same time, while here we can explain the idea line by line. But whatever is suitable to you, Doctor.
No, my job is to use whatever tools that I have to get the message across. So I prefer using both of them. I have also
like a mix of both would be nice.
Yeah. So this is the recursion slides that we were looking at. Today I'm looking at 2 more examples. Of course, in the slides you're going to find more examples, all right? But because of lack of time, I'm not covering everything. We looked at this recursion some. We saw this thing yesterday. So the runtime is linear, big O of n. Okay, now let's look at reversing an array. This is the code or the algorithm given to you. Here's the code given to you. All right. So I can go through this, or let's have a look at the Jamboard first. I'll try to understand what's going on, and then we'll look at the code. So imagine some array is given to you. Okay, these are the index positions. And I have some values here. I'll just put some random values. Doesn't have to be integers. Okay, so it's an array of type characters. What we want to do is we want to reverse it. When I say reverse it, okay, I mean this. B comes here, this becomes A. D comes here, this becomes C. F comes here, this becomes E. So you can see this is now in the reverse order. You read from right to left or left to right. Okay, so this is reversing the array. How to do this thing? Can you think of an idea, algorithm, how to do that?
What is the last step in the reversing? We can reach a base case.
Okay, so one approach is to create a temporary variable. Okay, let's call this thing temp. We're going to copy A over here. Okay, copy A over here. Then we copy the last one, B, and put it here. So this becomes B. And then I'm going to take this A and put this over here. So this is called switching. All right. Next, I'll go ahead and look at this one. So we go with C. C is going to go here. Okay. And I'm going to copy D over here. So this becomes D. Okay. And then C gets copied here. Okay. Next, extending the colors for understanding. So we're going to copy E over here. This becomes E. And repeat the same process. So we copy F over here. Okay, this becomes F. And then E goes back over here. Okay, so should I stop here or should I continue doing this thing?
No, stop it, Doctor.
So this is interesting. You need to stop in the middle. If you don't stop in the middle, what's going to happen is you're going to start switching everything back again.
Well, yes.
So we're going to switch E with F, and then this C with D, and then this A with B. So at the end, you're going to have the original array back. So that doesn't serve the purpose. So this means we need to stop in the middle. Okay, let's try to write code for this. Let's try to do this. So let's do it with the loop. Okay, try to do it with the loop. So I have some method public. Okay, it doesn't return anything. We don't have to return anything. And let's call it reverse. And we're giving it a array of type characters. Let's say the name of the array is A. Okay. Now we need to get the size of the array. Okay, so I'll say integer n equals a.length. Okay, I need to define this temporary variable. So we're going to say character temp. Okay, in the beginning could be empty. Next, what should we do? Can we use a for loop?
Yes.
So I need to go from 0 until the middle of the list. I don't want to go all the way until the end. So how do I stop in the middle? What should be my condition?
N
here?
over 2.
Very good. N over 2. And of
Make
course,
it equal, less or equal.
Okay, let's see. All right. Now we need to swap the values. Okay. So first thing, we'll say temp equals array of I. So it's going to take the value at 0. Okay. Put A over here. Next, we need to copy the last value over here. So how do we get the last value?
Size minus 1.
So I'm going to say A of I equals to A of last value, which is n.
Minus 1.
Minus I.
Yes.
Minus 1. Yes? Okay, dot length should give me 6 for this one. Right? So you cannot use 6. You have to say minus 1. And minus I, because minus I is going to change everything. This is what is controlled by the loop. Okay, so what's happening over here is n is 6. 6 minus 0 minus 1, yani 5. So we take b, we copy b over here in A of 0. Now we need to copy this value back, which is in the temp over here. So I will say A of n minus I minus 1 equals to temp. All right, so you copy this value back over here. And I think that's it. That's your for loop. And once the for loop is finished, your array is already in the reverse order. We don't even have to return anything. That's it. We're done.
Doctor, I didn't understand the last step, which is n minus I minus 1 equal to.
Okay, let's try to understand it with this example. So we're starting with A. Let's say in the beginning we had A over here, and this is B. So we start the loop. I is 0, I is less than n over 2, n is 6. 6 divided by 2 is 3. So 0 is less than 3. Okay, we go inside. You say temp equals A of 0. A of 0 now is A. So we go and put A inside temp. Now we say A of 0 equals to A of n. What's n?
Length, A.length.
Which is 6. Right now with this example, 6. 6 minus 0 minus 1. So A of 5, which is B. So we're saying go copy B over here. So we're going to go and put B over here. Put B over here. So this is B, and this is also B right now. Okay? Now third step is what we have in the temp, which is A. We're going to put this over here. So we say A of n, which is 6, minus 0, minus 1, and A of 5 equals to temp. So we go and put A over here. This becomes A.
Okay.
Now the loop goes back I plus plus, so now I is 1. So we repeat the same thing. So here's my temp. Okay. Temp equals A of I. A of I is if 1. If 1 is C. Okay. So we go and put C over here. Now we go over here. A of 1, if 1 equals to A of n, n is 6, minus 1, minus 1, because I is 1 now. So 6 minus 1 is 4, and A of 4 is D now. Okay, so we go put D over here. Copy D over here. Now this is D, and this is D. Need to copy back C from the temp to this position. So we say A of n minus I minus 1. So again, 6 minus 1 minus 1, which is A of 4, equals to the temp variable, which is A. Oh, sorry, which is C. So we go put C over here. Okay, I plus plus, I becomes 2. So again, repeat the same thing. So E goes over here, this becomes E. If I and A of 2 is equal to A of n, which is 6 minus 2 minus 1, yani 3, AF3. The AF3 is F right now. So we copy F over here, so F goes here. Okay, and then we say the same thing, A of 3 equals M. So we go put E over here. Okay, this is removed now. I plus plus, now I becomes 3. Okay, so technically we're supposed to stop here. If I do not stop here, it will bring back everything in the original position. So I need to stop here. So when this becomes 3, 3 is less than 3. So that doesn't work, it will not go inside, so we stop. So I think this condition is correct. We don't have to put an equal over here. This is fine. So far so good? Did you understand it?
Yes, Doctor.
Okay, let's try to do the, okay, just for the sake of practice, let's find the runtime for this. Can you give me the T of n for this?
Okay, so int n, you initialize a variable. That's 1.
So this is 1.
Oh yeah, this one. And then the
2.
2, Doctor.
This is 1.
So 2n plus 1.
So this is 2 and okay, be precise. This is not going to run n times.
No, this is n over 2.
n over 2.
So n over 2 and n over 2 is n?
It's n, yeah, so n plus 1.
N plus 1. Okay, this one. Fetch a value and store it. So this is
2.
And here, fetch a value and store it. 2. Okay, store this. This should be 1. Like, if you go into much depth, like we need to add this and add this, this is going to become too much, okay? We're just estimating. So we don't have to go and look at how many computations are done over here. So just keep it like this. Now remember, all of this is inside the loop. So altogether, can I say this is running 5 over 2 n times? Can I say that?
Yes.
Mm-hmm.
Yes.
Right, add it up. How many n's we have?
We will have 7 over 2n.
Okay, very good. And 1, 2, 3, 4, and 5, I think.
Plus
5.
5, yeah.
So big O is?
N.
Big O is n.
Doctor, in the int n is equal to either length, we say plus 1 times 2 plus 3. Is it still going to be 2 operations?
Which one?
Just an example. If we say int n is equal to either length plus 1 times 3 minus 2 times 4, that is still going to be 2 operations?
No, it's not, because every operation is going to take its own time. Okay?
Yes.
So what's going to happen is this 5 will change, it will become 7 or 8 or 10 or 100 or 1,000 or 1 million. At the end, it doesn't matter because this is just a constant term.
Yes.
Be concerned with the big O notation. Okay? So for big O, we only look at the highest order term. So we need to be careful with the n. Yani, if it is n, if it has to be n, it shouldn't be n squared or n cubed.
Right.
Okay, let's do the same thing using the recursive algorithm now. Okay? So, okay, I want to change this a little bit because we need to pass the index on. So say integer I. Okay, so there's always going to be a base case and the general case. So let's look at the base case first. Okay, so here let's define integer n equals a.length. If type, when do we stop?
When we reach the middle.
The middle.
When you reach the middle. How do I find the middle? They'll say I equals to n over 2.
Mm-hmm.
Okay, and then we reach the middle. If you reach the middle, we don't need to do anything. We just quit, return.
Yeah.
Okay, remember it's returning void, so we simply say return. Okay, else what we need to do is we need to switch the positions. So we used to define integer temp, equals to a of I. Okay, exactly what we did before. And then a of n minus I minus 1 equals to, I have to say a of I equals to this one. So we copy the last value and put it in the first position. Okay, and after this,
a n minus I minus 1 equal temp.
temp. Okay, and once you have switched the two positions, now we need to move forward. So recursive call, we're going to call this method again, reverse. Okay, you can even put a return over here if you want. Reverse a, and I'm going to say I plus 1. All right, that's it. So what's going to happen now? Let's look at an example. So here's my original array.
Doctor, does it matter if you do I plus 1 or I plus plus?
Yes, it does matter. I plus 1, what's going to happen is going to compute it and then call it. If you put in I plus plus, that's a problem. Okay, it's not going to compute it. It will pass I, which is going to create an infinite loop, infinite recursion.
Oh, okay.
Be careful in recursion. Never use I plus plus. If you want to use plus plus I.
Oh, okay. So we can do plus plus I.
Okay, so these are my values. Now what's going to happen is, let's say we call this method here. So reverse a, and let's say we start at 0. Okay, so we go here, we get the n is of course 6. If I equal n over 2, type is not. So we go here, we say integer temp. So here's my temp. We'll go put a over here. Okay, then we go put, like before, so 6 minus 0 minus 1. So we're going to put f over here, so this becomes f. And then we say this position equals temp, so this becomes a. Okay, now what's going to happen is when I call this again, so I'm simply calling reverse a, and I'm going to pass 1 now. Okay. So call it again. Now I is 1. So 1 is equal to 3? No. So again, we repeat the same thing. So b goes here. This becomes b. Okay. And e goes over here. So this becomes e. And then b goes over here. This becomes b. Okay. And then we come to call reverse with a plus 1. So this becomes reverse a of 2. So what I'm building in front of you, what do we call this?
Link.
Yesterday. This is called a recursion tree. Okay, recursion tree. Okay. Next, so we're going to call with A2. So what's going to happen is with 2, C comes over here. So this becomes C. Okay, so we replace D over here. So this becomes D. And then we copy C over here. After we're done with this thing, we're going to call reverse A3. Okay, again, when you call it, it goes over here. So 3 equal 3, yes, return. Return means it's not going to call anymore, so it'll just go back. When it goes back, there's nothing else after this. So it'll go back, and we're done. Okay, whoever called it, going to get the return value, which is nothing, which is void. So the array is traversed. Now, if somebody asks you, what's the runtime for this? Let's try to estimate it. So how many operations is this?
We have 1 here.
Fetch a value and then store it in a local variable. So I believe this is 2. Okay.
What about the
n over 2, Doctor, here?
How about this one?
But 2 n over 2. So
No,
it will be
wait.
n.
Oh, wait. We'll come to that after. Okay, just do this thing. Okay, how about this one?
It will be, I
One.
think, no, not 1. We'll n over 2 multiplied by 2 because we fetch and compare.
No, this is the local variable, so this is already available to us. We're not fetching. So
So-
n over 2, this is one operation, and compare, that's two operations. Okay? So every time we call this method, it's going to execute these two lines for sure. How about this line?
1.
It works only one time. Okay, so for now, just forget about it. Okay, let's go to the else part. So either it's this or this. It's going to execute this every time. Okay, but it will come over here only once. The rest of the times it's going to go to the else. So let's try to see how many operations are these. I think we did this before. We estimated this to be 5, right?
Yes.
Okay, so let's assume this is 5, even though maybe there's a bit more. All right, how about here? Recursive call. Can I say this is 2 operations?
Yes. The return I plus 1.
So return and I don't know, the return call itself plus 1, this one. So this is 2 operations. Let's say this is 2 operations. Okay, so altogether, how many operations are repeated? Okay, so this is 5, 6, 7, 8, 9, 10, 11. I can say this is 11 multiplied by 5. How many times are we calling this? Are we
n
calling
over 2.
times
N over
or n over 2? So n over 2. Okay, so it's 11 n over 2 plus constant plus this one. This is only 1, so we're assuming C is some constant, so C plus 1 is still C. Okay, we don't have to write plus 1. So this is my estimated runtime. So big O is still big O of
N.
n. Like which program runs faster, this one or this one?
This one.
Okay, can you compare them?
I can. I think the same.
It's 11.
That one is 7 over 2.
And this is, oops, this is 7 over 2. Okay, but obviously this one is running a little bit slower than the other one, but the big goal for both of them is exactly the same. Right? Can we optimize this further? Can we make it faster even more? Look, what I can do is instead of computing this, I don't have to put it over here. What I can do is I can create another variable over here. I can say integer n. Okay, that is the size of the array. So you can pass 6, 6. It doesn't change. 6, 6. Now I can get rid of this line. I don't need it. Is this going to save 2 more?
Yes.
So this will become 9. Okay. Now you can think about removing something else from here. That can make it a bit faster. Anyways, so there's always room for improvement. You can always relook at your code and see if you can improve it. All right, let's look at the next example now. So this was the reverse array. Okay, so the runtime for reverse array is big O of n. Let's look at compute powers now. Okay, this is just another example. Compute powers. Okay, here's an example. If I give you 2 to the power 5, this is the same as 2 times 2 times 2 times 2 times 2. Okay? So all I have to do is just keep multiplying it 5 times. That's all. So can we write a program that if I give it 2 values, if I give it the 2 and the power, it will compute the value and return the integer value. Can we do that? Let's do this
Yes, doctor.
with the loop. Okay, so public type is going to return integer.
I think it's simple with the recursion.
Let's do this thing with the loop first. Okay, integer. What do you call this? Let's say this is x and y. Okay, let's go with x and y. So you're going to have x, y. So x multiplied by until y number of times. Okay, so how to do this? You need a loop. Let's create a value starting with 1, integer m equals 1. We're going to use a loop, integer I equals, it's up to you, you want to start from 0 or 1?
1.
Okay, just to make life easier, let's go from 1. And as long as I is less than or equal to y, I plus plus. Because I'm starting at 1, so I'm putting an equal over here. So you're going to say m equals m multiplied by x. Okay? And we're going to do it this many times. And at the end, we're going to return m. Oops. There you go. That's your program. Is this going to work?
Yes.
Yeah. So if you put 2 to the power of 5, so m equals m, which is 1, multiplied by 2. So this becomes 2. Next time, 2 times 2 becomes 4. Next time, 4 times 2 becomes 8. Next time, 8 times 2 becomes 16. Next time, 16 times 2 becomes 32. So 2 to the power of 5 is 32. It's going to return 32. That's correct. Type. Estimate the runtime for this.
Okay. First one has 2 operations.
2 operations here.
Then 1 operation here.
Yeah, here.
Here we have y.
2n plus 1.
So 2n plus 1.
Okay.
Okay.
But there's
here.
no n, so it's y.
Yeah, n is the, let's say this loop is running n times.
Okay.
Let's say the value of y is n, very large value. Okay, how about this one? 2 operations.
Yes.
Yeah, 2.
And this one? 1 operation.
1.
This is, yeah. So now the overall runtime is 4n plus
5.
5. Yes. So they go off n.
Doctor,
Yeah.
why we count integer x and integer y for the operation, but in the past example we didn't.
Oh, we did not? We should have. Yeah, we should have. We should have done it. Okay. Okay, let's try to do the recursive mode now. So we'll have the same thing, public integer power, we're going to pass it integer x, integer y. Okay, and we need the loop variable, which is I. So let's go with I. Okay. When did we stop the loop over here? We can use the same thing for the base condition. So if I becomes bigger than?
Doctor, I think it's possible to do it without
what?
the I. Without the I.
No, you need a counter. Without the counter, it will run infinitely.
Yes, right.
Okay, so if this is the case, we're going to return.
But we can do it in a descending order.
Yes, we can. Of course.
And make the base case, if the y is the power, we can make it, if it's equal to 0, return 1.
Yes, we can. We can do that. Of course, it can be done that way also. Okay. So let's do this one. So here's a base case, return something. We didn't write anything yet. Okay, else what we should do is
X or I equals.
we're going to say return x.
We can say n
multiplied by power x, y, and I plus 1. Okay, so that we're starting from 1. Yes?
Yes.
Okay, but what do we return here?
What do you
Return
return?
1.
X. Don't you return X? Because X is the one changing.
Yeah, last thing would be X. So we return X. Or should we return 1?
Should we return 1?
Yeah. Should we
One,
return? Let's see. Let's try to build a trace and then see what happens. So we go with power. Okay. Let's say we're passing 2, 3, and in the beginning, I should be starting from 1. Yes. Okay. So I1 is bigger than Y. No, it's not. Y is 3. Okay, so we go over here, return. We're going to say X, which is 2, multiplied by power of 2, comma 3, comma 2. Okay. We call this thing again. Now I is 2. So 2 is bigger than 3. No. So we go over here. We'll say 2 times power 2, comma 3, comma 3. Okay. So again, we call it again. So now this is 3. 3 is bigger than 3. No. So it's going to go over here. And it's going to do 2 times, oh, sorry, power 2, comma 3, comma 4. Okay. Now when it goes over here, this is 4. 4 is bigger than 3, yes. So it's going to give you
1.
All
2
right.
times 1 is 2.
Now we start returning. We start returning back. So that's going to return back. This will become 2 times 1 is 2. Okay. So this becomes 2. So this will be 2 times 2 is 4. This one becomes 4. Okay. So this one would be 2 times 4 is 8. It's going to return 8. So this method gives you back 8. Is that correct? So to the power 3 is 8. Okay. So the code that we've written over here is okay, but we can improve it, of course. This is not the end of the world. We can improve it. But let's try to figure out the runtime for this. So how many operations are we doing here?
3 in the first one, power.
Remember when I'm comparing this one with this one, here I computed this as 2 operations. So I need to do the same thing here. So this would be 3 operations. Here, 1 operation. This one happens only once, so we're going to consider this as part of the constant. And here, this is multiplication.
Yes, 1 and then
multiplied by recursive call. And if you want to consider this, so let's say this is 3 operations. Okay. So 3 plus 1 plus 3. So that's 7. Okay. Plus, so 7. And now the trace is going to give you an idea. How many times did you go down? If that is equal to n, this means the runtime would be n. So here, the value of y is what is changing this. So we did this thing 1, 2, 3 times. Okay, 3 times. So the last one we shouldn't count because that is a base case. So we started from here. So 1, 2, 3. We counted 3 times. So this is n. So that's my runtime. 7n plus c, which is big O of n. So which one ran faster? This one? Or
the other one?
So this is 4n plus 5. This looks faster compared to this. Can we improve it?
Yes.
So somebody was suggesting that we don't have to put an I over here. We can work with a 1. We can go the other way around, make it 0. So this way, you're going to get rid of 1 of this, and you're going to get rid of 1 of this.
Yes.
Okay. So that's going to make it 5 of n. If you do it that way. So 5 of n plus c, which is still slower. Yeah. But again, the big O is still the same. All right. Let's look at the last example before we look at the tutorial. Okay, so the runtime for this one is also linear, big O of n. Okay, let's look at the Fibonacci numbers. I'm sure you've studied this in math somewhere. Did you guys? Okay, Fibonacci is a simple formula. So Fibonacci of 3 equals to Fibonacci of 2 plus Fibonacci of 1. I don't remember if this is plus or minus. Let me see. Okay, again, in the slides, there's many other examples, but I'm just jumping over it. You don't need to know everything. Yes, it's a plus. Okay, so Fibonacci of 2 would be given by Fibonacci of 1 plus Fibonacci of 0. It says that Fibonacci of 1 is 1 and Fibonacci of 0 is also 1. All right? So given this information, the formula given to you, if somebody says find the Fibonacci of some value, let's say 10, so according to the formula, Fibonacci of 10 is equal to Fibonacci of 9 plus Fibonacci of 8. Now to find Fibonacci of, you cannot compute this thing unless you know these values. So to find Fibonacci of 9, we have to do this. Fibonacci of 8 plus Fibonacci of 7. Okay, again, we don't know this thing, so you have to go and find it again. Fibonacci of 7 plus Fibonacci of 6, and so on. Let's try to do a trace for a simple one, Fibonacci of 4. Okay. So let's look at the recursive algorithm first. So public integer Fibonacci, and we're going to pass it some value, integer x. Okay. So again, let's do the recursive one. So when do we stop? Either the value becomes 0 or 1. So if x equals to 0 or x equals to 1, we're going to return 1. Else, okay, we're going to return, it's a recursive call, Fibonacci of x minus 1 plus Fibonacci of x minus 2. Okay, and that's it. That's your entire code. Now, if you're trying to do a trace for this, okay, let's try to find the runtime first. Okay, so to do the runtime, we need to find the trace. Let's do the trace. Let's do it for 4. So if somebody calls Fibonacci of 4, okay, x is 4. So obviously this is not true. So we go over here, we're going to say return Fibonacci. So we're going to say Fibonacci of 3 plus Fibonacci of 2. Okay. Now, problem is we don't know Fibonacci of 3 or Fibonacci of 2. So we have to call this again, twice now. We have to do this one and this one. So if I call Fibonacci of 3 again, what's happening is, of course, this is not true. So it will go over here. So that's going to compute Fibonacci of 2 and Fibonacci of 1. We're not done with this side. So let's try to do the right side now. So I can call Fibonacci of 2. Of course, this is not true. So we go over here. Just going to call Fibonacci of 1 and Fibonacci of 0. Okay? So now what's happening is the computer is not going to go like this. Okay? It goes in one direction first. So we go and complete all of this first. So let's try to do the way the computer would do it. Okay, so Fibonacci of 2 will do Fibonacci of 1 plus Fibonacci of 0. Fibonacci of 1 is going to be the base case, so that's going to give you 1. Okay, so we stop here. Once you stop over here, we go and look at the right side. So this one is going to give you 1 again. It's also a base case. So we were able to compute it now. So 1 plus 1 is 2. So the whole thing, whole of this, is giving back 2. So this becomes equal to 2. Once we've found this, we can go and look at the right side. Now this is Fibonacci of 1. When you call this thing again, that's a constant value because that's the base case. So it's going to return this back over here. This is equal to 1. Now you find these two values, so we can compute these two. Okay, so 2 plus 1 is 3. So it's going to give you back 3 over here. Okay. Now again, we cannot compute this unless we do the right side. To do the right side, okay, repeat the whole thing again. So Fibonacci of 2. So it's going to give you Fibonacci of 1 plus Fibonacci of 0. Like, don't you think we've already done this before? Somewhere?
Yes.
Yes, done.
We already did that.
1, 1, 2.
Problem is the computer is not smart. It won't be able to understand that it has done it. Your algorithm is not smart. So it will still go and compute it. So it will go and find this. It's a base case. You'll find 1. That's a base case. 1 plus 1 is 2. It's going to give you 2 back. Okay. Once you get 2 back, so now you'll be able to compute it. So 3 plus 2 is 5. It's going to give 5 back, and then 5 would be returned. All right. So what kind of function is this? Just looking at the trace. Does that look linear to you? How many recursive calls did you make?
A lot. Exponential, maybe.
So this is 1 recursive call, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and there was a original call. So we did 13. Okay, for 4, we did 13. I tried to do the same thing for 5. What's going to happen?
Yeah, it's going to exponentially increase with the number.
So this will become 4 and 3, or it will become 3 and 2. This will become 2 and 1. This will become 1 and 0. Okay, this will become 1 and 0. This will become 2 and 1, 1 and 0. Okay, imagine doing this thing for 6. Okay, for 6 it would be like this. And repeat the whole thing again. So 3 and 2, and 2 and 1, and 1 and 0, and 1 and 0. Okay, so look how many recursive calls are there. Every time we're creating 2 more recursive calls. 2 more recursive calls. If I assume this to be a very large number, we're going to get something like this. Okay, it's a triangle. And every time the size is increasing by 2. Okay, so we have 2, then becomes 4, then becomes 8, then becomes 16, then becomes 32. Okay, so if you have a shape like this, it's creating a triangle like this, every time it's increasing by 2, you can say this is
exponential.
Okay, so we go off 2 to the power n.
Yes.
If you just look at this, you won't be able to see it. Okay, you have to actually go and trace it to be able to see it. If you just look at this, this is 1 operation, this is 1 operation, this is 2. We have 2 recursive calls, so I don't know, this is 5 operations maybe. Okay, and this is maybe 2 operations. So altogether, this is 5. We would be happy to say 5n plus c. Like, we have to be very careful here. You need to trace it. If you're not able to trace it, you would give something like this, which is wrong. Okay, so the runtime for this one is exponential. All right, we've looked at some examples. Again, this course is not about looking at all possible things. So just to give you an idea, that if you have a recursive program, look at the code, try to create a trace, a recursive tree. Okay, and from here, you try to guess what's the runtime. So again, quickly, for linear, it's easy. You're going to get a trace like this. Okay, for logarithmic, what did I tell you? How can we guess the runtime? If every time the size is decreasing by 2. We looked at one example only, which was binary search. So if the size was 16, next step becomes 8, next step becomes 4, next step becomes 2. So if the size is decreasing by 2 every time, this is logarithmic. Okay, and yeah, linear, we've seen 3, 4 examples now. All right, so we're done with Fibonacci numbers. the runtime for this one is exponential. Let's look at the tutorial number 5. Okay, any questions before we go there? Okay, so we have some other examples. There's multiple recursion. If you want, you can go ahead and look at it. Okay, puzzle solve. There's another example. So it's up to you. If you want to go ahead and look at it, that's fine.